is my greatest pleasure to introduce Professor Nobuaki Obata from Tohoku University. And he is the leading mathematician in quantum probability from Japan nowadays. And he has published 3 books that I am aware. And the first book, which is about Weimer's distribution theory, I read it completely for my PhD dissertation. It was the one for which I learned about pi noise. And without it, I could have not done my research and couldn't get my PhD degree. So it is my greatest pleasure to invite Professor Obata, to have Professor Obata as to introduce Professor Obata as a colloquium speaker, and he will speak about asymptotic spectral analysis and growing gas. Please.
Okay, thank you very much for a kind introduction. And also I'd like to thank the organizers of this colloquium. And I am enjoying very much the stay in the Ohio State University just for 1 week. Well, I enjoyed very much with also the snow and coldest temperature. And also I thank the MRI Institute for kind support. Thank you very much. And I'd like to start with my talk. But before that, I'd like to introduce myself a little bit. I am coming from Sendai City in Japan. In Sendai there, and there is a Tohoku University that is the 3rd oldest national university of Japan, and about 110 years old, not so old compared to a university in the United States. But in Japan, it is the 3rd oldest. And that is very, I'm afraid that it's a very weak image. But there is America there, actually. And that indicates almost, so Sendai is here, but San Francisco, Washington, D.C., Athens, and the list of that is almost.
To get to America, you have to go through Portugal?
We have a very close connection with Portugal in history. Anyway, and I am working in Graduate School of Information Science. That is not the Department of Pure Mathematics, but that is one of the 17 graduate schools. And it is relatively new institute because computer science and information science is relatively new field, but very active. So it is about 25 years old. And myself serving as professor since 2001. And before that, I worked in Nagoya there. And those times I belonged to the Department of Mathematics. And my major research interest already Professor Stan kindly introduced, but spectral analysis of graph, random graph, quantum probability, quantum Whitman analysis, and anything related to network science. That is my current research area. Okay. So today, I'm a little tough. Can you see? Okay. Main theme of the discussion today is a growing graph. Growing graph is just intuitively a graph. We have a graph, but as time goes on, it grows and it becomes bigger and bigger and bigger. Such situation is in mind. And also, I am interested in the spectra of graphs.
But there is some law how it grows.
That is just an intuitive. Wait, later I will explain. Now, by the way, spectral analysis of graphs aims at the analysis of graph in terms of matrix. But not only matrix, we are interested in the, for example, eigenvalue distributions or spectral distributions. So that relationship is very interesting and also has a long history. So I like to analyze the growing graph in terms of spectra. That is my thing. And also I use, okay, here, just I asked the question. So growing graphs, we need to formulate more or less. So in this talk, I think 2 ways of growing. One is just a repeated application of graph operation, for example, graph product. If you have a concept of graph product, then you can repeat many times, then we get a bigger and bigger graph. That is a growing graph. Okay? And or if you have a family of graphs, and that family is indexed by certain parameters, alpha, beta, gamma, and so on. And that family is infinite family, then we may take out suitable parameters, and we can consider this is a growing graph. Or if you, of course, there is no time axis. Therefore, just I am interested in the asymptotics of large graph. That is the same thing in my case. And what I am discussing is just taking adjacency matrix and consider the mth moment in certain state. I will explain later. And this quantity is more or less algebraic subject, object, but the mth moment of A, we say, and that is represented by certain integral of this type. The right side is mth moment. So if you have such identity, we say that mu is a spectral distribution.
So on the left, it's not power n, it's just index for n.
Okay. I will explain later, but this symbol is just a so-called state, linear function. Positive linear function.
A to power n. Is it
A to the power n.
Is it genuine power of an A to power?
A is a matrix.
Yes.
This is A to the m. A to the power m is just unit matrix.
Okay.
And for that matrix which has some scalar, this is a linear function. Okay, in that, so growing graph is formulated in that way, and we are interested in spectral distribution of adjacency matrix. That is what I am going to talk. Now we are coming into the more precise part. And I employ the techniques in quantum probability, which is less common here. So I like to introduce quantum probability very shortly. Okay? And then we are coming into the main discussion. Okay, so quantum probability, in other words, non-commutative probability or algebraic probability. According to your taste, people call it in a different way. And these three books are very typical in this area. Okay, so how quantum probability works, I will explain by using a very simple example. That is coin toss. So just think coin toss. Coin toss is just a very simple random phenomenon and modeled by a random variable. That random variable having two values, let's say +1 or -1, according to heads or tail. Okay, and probability is 1/2. Therefore, first line is just a definition of random variable x, and using that x, we can model a coin toss. But in fact, it is not very important which probability space we employ. More important thing is just a distribution of x. So this distribution is just a 2-point combination of 1-point mass. Okay? So it is very simple distribution, but it gives you the statistics of the coin toss. So actual computation mostly depends on the moment sequence. Okay? So moment sequence is a very important characteristic of coin toss. Okay, let's compute. It's very easy. The mth moment of this probability distribution, just the integral of this. But measure is this. Therefore, we have the moment sequence mn is equal to 1 if m is even, otherwise 0. It's very clear. Okay, that is moment sequence. And if you have a moment sequence, you can recover statistical properties of coin toss. That is a cluster story. Okay, now let us think the matrix A, 2x2 matrix, 0, 1, 1, 0, and canonical basis, 0, 1, 1, 0. Okay. Now let's compute the inner product of E0 with a to the power m E0. Because a to the power 2 is identity matrix. And A sent a vector E0 to E1. they are orthogonal to each other. Therefore, this quantity easily computed is equal to 1 if m is even and 0 otherwise. It's very trivial. But you remember, this is exactly same as the moment sequence of this distribution. In other words, here we have another model of coin toss. Another model means we can model coin toss by using matrix. So we are really using a to the power m. Therefore, we have actually algebra. So let's consider the a, that is some algebra generated by a, actually polynomial in a. And then we have a linear function phi of a, defined by this formula. This is the matrix element of a. Okay. And then that matrix A models the coin toss. And I say a algebraic realization of the random variable x. The x is the model of coin toss. Okay. Now, you see, in that way, coin toss is a classical random variable, but we have another model that is in terms of matrices. And there is a merit here because this matrix A, that A, is decomposed into two parts, trivially, but this is so-called quantum decomposition of the random variable. This is quite easy because this is A plus and A minus that acts on the canonical vectors very easily because A plus sent E0 to E1, A minus sent E1 to E0. So that kind of decomposition. But for any real random variable, we can introduce quantum decomposition. And these two matrices are non-commuting. Non-commuting, of course. Therefore, we have here non-commutative structure. So this is a message from this observation that every classical random variable, behind that, we have some non-commutative structure. And the non-commutative structure is sometimes useful to analyze the property of this random variable. That is.
So it sounds almost like a theorem. Right? That's here it's observation, but what you said is a theorem that always can do non-commutative.
Yes. That is theorem. That is theorem. This is the example.
Yeah.
Okay, now a little bit more axioms. So quantum probability based on the algebraic probability space, that is a pair of A phi. A is a star algebra over complex number fields. And there is a multiplication unit and a state. The state is linear function and positive, this property is positive, and normalization. So such kind of linear function plays a role of probability measure in classical probability theory. And then if you have a real random variable A in A, namely symmetric or self-adjoint, such element is called real, then we can find out always a probability distribution mu satisfying this identity. Left side is an algebraic probability space. Right side, classical distribution appears. This is linking these two concepts. And this mu is called the spectral distribution of A. The existence is proven by using Hamburger theorem. This is a classical theorem for moment problem. But notice here that mu is not necessarily unique because of the so-called indeterminate moment problem. That is a problem around the moment sequence. But anyway, always exists. Therefore, we are interested in the precise or explicit form of mu for a given random variable.
C is a bounded linear function.
No, I have no norm A. Therefore, we don't say bounded condition. But you know, the positivity gives you some bound. Okay.
But it doesn't require unique.
Because an A is, we have no topology on A. This is purely algebraic. So we don't say continuous linear function, or we don't say a bounded function. Just
The event is positive definiteness. That's why it's very close to Bochner or Terbor's theorem. Right? It's the same.
yes, yes, exactly. This is it. This is just a table of the correspondence. So in a classical probability, we are working on the measure space, but instead we are working on the algebra and state. Random variable is up here just a function, measurable function, but here an element of algebra. Expectation value is computed by using integral, but here we have no integral, but instead we have phi. This phi gives you expectation value. Then we can define a moment, but we don't have such a distribution function. We have only polynomials, so we cannot get this kind of indicator function, like a step function. So we are working mostly on moment. And here, classical probability, we have independence. So if x and y are independent, we have this formula. But for non-commutative case, there are many variations. And large numbers and the central limit theorem formulated by this kind of limit. But this is similarly, we can formulate here. But a limit distribution different. I will explain later. So this is the last correspondence. So instead of classical probability, I like to work on quantum probability. Particularly, I like to apply this technique to spectral analysis of glass. Okay, now I come into the main part. So the first one is just a definition, formal definition of a graph. Everybody knows. Just V is a set of vertices, E is a set of edges, and if x and y are connected by an edge, we denote x to the y. And then we define adjacency matrix A. This is a matrix indexed by vertex set, and if x and y are adjacent or connected by an edge, the value is 1, otherwise 0. Very simple matrix. Okay, very simple matrix, but it has all the information about the graph. So if you are given an adjacency matrix, you can recover the graph structure uniquely. And for technical reasons or natural reasons, I assume these two conditions. First one is the graph is connected. And second one is so-called locally finite. We are dealing with also infinite graph, but we assume that every vertex x has finite degree. Finite degree means every vertex has at most finitely many edges. Otherwise, we cannot define the algebra. So that is crucial for the next definition. So now, given a graph, then we have adjacency matrix. Then we consider adjacency algebra that is generated by the matrix A. In fact, the adjacency algebra is just a set of all polynomials in A. Now, this adjacency algebra is a star algebra. Therefore, if you have a star state phi, then we consider the adjacency matrix A as a real random variable in quantum probability. So now we are almost prepared the situation where we can apply quantum probability. So which kind of state is interesting? I am so far studied 3 kinds. The first one is trace. When the graph is finite, we can define the usual trace. Usual trace, I mean just the sum of diagonal elements. But divided by V, that is the normalization to have the identity. If A is identity, the trace state gives you 1. That is normalization. So we need to divide the number of vertices. According to the general theory, we know this identity holds for certain measure. In that case, this mu is nothing else but eigenvalue distribution of the matrix A. So eigenvalue distribution, eigenvalue of matrix A is very interesting object. But we are dealing with the eigenvalue, not a single matrix set, but we treat with as eigenvalue distribution, probability distribution. Okay. And second one is just a vacuum state. We say we take a certain point O, and we consider the matrix element of A at O. Then it becomes a state. And again, we have this identity. This state is given by this probability distribution mu. But by simple observation, we know that this quantity, mth moment, this is the definition. Because of the definition of the adjacency matrix, this gives you exactly the number of m-step walks. So this case, m-step walks, that is the combinatorial number, is expressed in terms of integral. That is point. And also we are interested in the deformed vacuum state by using Q matrix. The Q is a parameter and P is a graph distance. So this is a deformation by using small q. And this is also interesting, but I don't go into detail today. Okay. So now this is the main problem and the basic technique. So main question is this. So we are given a graph or a growing graph and a state on the adjacency algebra. Then the main question is find out a probability distribution mu satisfying this identity. For a growing case, maybe this is asymptotically equal. So we need some normalization. So, but anyway, asymptotically equal, then we like to find out mu. That is a spectral distribution. And today we are discussing this kind of question from 2 points of view. The first one is a use of various concepts of independence. In a graph product case, actually, the adjacency matrix A is decomposed into certain parts. But these are, if these satisfy certain good reactions, we can compute A, this probability distribution, in terms of B. And the second method is a quantum decomposition. I already mentioned a very simple case, but this A, adjacency matrix, also is decomposed into 3 parts, non-commuting parts. But this decomposition sometimes useful to get this spectral distribution here. So I like to discuss 2 aspects of that main problem. Of course, if you are interested in more general situation, maybe you can do. I haven't yet done so actively, but of course, an adjacency matrix is a very special matrix. And you can relax the conditions, of course. 0, 1 value, symmetric, diagonal 0. From that aspect, you can generalize the situation. Then you obtain graph with loops. This is loops. Multigraph, multi-edges. Digraph, directed graph. So we have orientation. Or further generalized one called network. But to some extent, the situation is similar.
But on the previous page, as you said, if you know the spectrum, then there is no problem. If you know the eigenvalues, then that's it.
Okay. Not always eigenvalue distributions, but if you take trace, for example, left-hand side, if you take trace, then this mu is nothing else eigenvalue distribution. So of course, if you compute directly eigenvalue of A, then you get this. But there is another way of computing that. And also there are many matrices associated to a graph. Adjacency matrix is the one basic one. Also, Laplacian matrix is very important, and there are many. So, of course, you can discuss some similar questions to those matrices. So I don't go into that. Okay. Now, this is maybe an interesting part of quantum probability. We have many different concepts of independence. If you know classical probability, you know the independence. For example, the first tossing, second tossing, independent. That is quite easily understood from the daily life too. But in non-commutative situation, we have many others. And I like to relate those different concepts of independence to graph product. So any binary operation is a graph product. So if you have a graph, two graphs, somehow you are combining them to get big one. So that is graph product. In terms of adjacency matrices, A1 and A2, then you get big matrix, a kind of operation on matrices. Then if you repeat the graph operation n times, then we can define the n power. Then this gives you a simple construction of going graph. So we like to study the asymptotics. So first one is Cartesian product. That is the most basic one. Cartesian product or direct product. The first line is just a formal definition, but this is just a picture of direct product. That is everybody knows. Okay. You have these three planes here and here, plane. So this is the usual one. Okay, that theorem is the starting point. So how the adjacency matrix of direct product look like? Adjacency matrix acts on small L to B. This is just a vector space over B. But the V is now the direct product, therefore V1 times V2, and we have a canonical correspondence between these two spaces. So using the tensor product, so adjacency matrix A is decomposed into two parts. This two. I is identity matrix. Then we can say the right side is the sum of independent random numbers. But I say many type of independence. So here we say commutative independence. So a special type of independence in quantum probability. So for a growing graph, n times n-fold power, then the adjacency matrix looks like this. Here B is adjacency matrix of G. So this is sum of commutative independent random values. That is starting point. Okay. Now, what is commutative independence? We have algebraic probability space. We are working on the real random variables. Then we say this sequence is commutatively independent if the following conditions satisfied. We take out m element of this sequence. Okay, but these are maybe same, so we take out the different ones like this. Then we like to consider the mixed moment of this element. This number is called the mixed moment. Then they appear the same thing sometimes. Therefore, we can write up like this. Then factorization. Of course, if you know the classical case, this is exactly the rule of the classical probability. How to compute the mixed moment for independent random variables. But here, AN itself are not necessarily commutative. After taking state, it happens. Then we say these are commutative independent. Then for commutative independent, we have a central limit theorem. They're normalized as usual, mean 0, variance 1. And if they are commutatively independent, we have the following limit formula. Left side is exactly the usual quantity appearing in central limit theorem. And we are computing an mth moment and taking a limit. Then that is exactly the mth moment of the Gaussian measure, normal 0, 1. Okay. For each AN, we don't discuss distribution. Only we assume 0, 1 normalization. But limit is always Gaussian. So we can prove that by using combinatorics or other technique.
I'm sorry, does this commutative theorem imply the classical one?
Yes. That is just almost a parallel thing, translation from the classical case to
so that's almost the same.
almost same. Only the remark is that AN may be non-commutative. But after taking phi, it looks like commutative random value. So applying the case of the Cartesian product graph we have, this is just a normalization of the adjacency matrix, n power case, nth moment going to Gaussian. And also spectral distribution is computed by using convolution. That is the usual thing. So, okay, that is not so interesting. So now I introduce another product. It is called COM product. The formal definition there, but it's not so easy to see. So look at this. It's much easier to see what is going on. You have two graphs. These are not symmetric. Okay? We take this square as a base and attach this second graph, this is a triangle, to each vertex of this base graph. That is called COM graph, COM product. Therefore, G1, G2 not commuting. Now, adjacency matrix looks like this. Adjacency matrix of COM graph is a sum of two. But you see, A1 adjacency matrix of the first graph, A2 of the second one, identity, but here not identity. Here new one, this is projection. We have fixed one vertex O, then P2 is just the orthogonal projection onto the space spanned by O. So this is rank 1 projection. If you repeat this procedure, then you get this expression. First, identity happens, adjacency matrix appears, and projection. this is a new type of sum. And now, this is important because these components, there are n factors, they are independent, but we say it is monotone independence, new independence here. So I will explain monotone independence. Okay, in quantum probability, we are dealing with algebra. Then how do you formulate independence? This is the one way of the formulation. Independence gives you a rule of factorization of the mixed moment. Here, again, A1, AM are elements coming from these algebras, subalgebras. Sometimes the same algebra pairs and so forth. Okay. And we have an ordering of that family of algebras. Okay. And then here we see each A1, A2 belong to certain algebra. So the algebra has certain index. If the index makes a peak, then we allow factorization. Okay, now here is a picture. We like to compute this mixed moment. Only I take the numbers, okay? Because here A1 belongs to number 2 algebra, A2 belongs to number 1 algebra, and so forth. So this is just a graph of these numbers. The factorization rule is new here. If you have a peak here, then you can factorize. So 2 is a peak, therefore you can factorize 2. 4 appears as a peak, therefore you can factorize 4. This 4 again peak, therefore factorize. 6, 6, together one peak, therefore we can factorize 6, 6. We cannot separate no more, okay? 6, 6, and so forth. In that way, we can introduce the factorization rule. If this happens, then we say they are monotone independent. And we can discuss the associated central theorem. So this is the answer. This was done by Nobuaki, Japanese. And this is the central theorem, as usual. If AIs are monotone independent in the sense, the limit distribution is this. That is arc-sine law. It is also famous probability distribution in probability theory. But here appears arc-sine law looks like this. So totally different from the Gaussian. And then applying this situation to n-fold monotone, excuse me, this is star. A monotone product means a cone product, I'm sorry. N-fold cone product graph, this one. Then the limit is arc-sine. So that is another asymptotic spectral distribution obtained from the product structure.
1 is 2, not 1, not 4. 2 minus x squared.
Oh, yes.
How do you count? Not 1 and not 4.
Okay. Because of the normalization. If I remember correctly, this gives you variance 1. Because this is a normalized 1. Therefore, mean zero variance 1. One more example, the star product. Star product is a more simple product. If you have two graphs, you can join at one vertex. Then we have new graph. That is a subgraph of the direct product graph. And that is star product.
But this depends on the number of the verses.
Of course. Then the adjacency matrix of A is decomposed into two components. A times projection times A. Then they have very special relation, and we call it Boolean independent. So repeated application of this star product gives you this kind of operators, matrices, and they are Boolean independent. I don't give the formal definition of Boolean independence today, but you can imagine now there is some special rule of factorization. And after that definition, we can prove the central limit theorem. Then in that case, the central limit measure is just a 2-point distribution that appears in coin toss. It is very strange. Central limit measure is just a 2-point. And also we can apply that argument to star product graph, then we get that asymptotic distribution. Actually, there are, if you open the book of graph theory, there are many graph products. So here I mentioned already, but another product, something different happens. And they are all already combinations. The final one I didn't discuss anything about, but that is free product. That like a free group. So in that case, we cannot describe in this way, because if you take free product, then the graph becomes immediately infinite, like free group. So, but here also we have some convolution that is called free convolution. And around this, we say free probability theory, and mostly started by Vogelsky, and that is very popular now. But anyway, we can discuss like this graph product. Okay, so this is just a table. Particularly, we have a commutative independence, monotone independence, Boolean independence, and free independence. I didn't know that. Okay? But then a central limit measure looks like Gaussian, arc sign, 2-point distribution, and Wigner's tensor. This different distribution is obtained from different independence. And also different independence is related to certain graph products. Therefore, we can apply these situations to spectral analysis of graph. Okay, so this is the independent part. And then I like to, in the last part, I like to discuss the method of quantum decomposition. So, now we think a graph G, and we fix an origin O. Here is the origin. And then a graph looks like this. Okay, if you have a graph here and one vertex, if you pick up here, then more or less you have this kind of structure. This is called the distance partition or stratification. Actually, Vn is just a set of vertices which has distance n from origin. Corresponding to these subsets, we associate unit vectors defined by this. This delta x is a canonical vector corresponding to this x. They have disjunct support, therefore this is the orthogonal sum, and we get Hilbert space. This Hilbert space is denoted by gamma of G. And now adjacency matrix. Adjacency matrix tells you what are your neighbors. Here you are here. Then your neighbors are always upper floor, lower, or in the same. It's trivial, okay, obvious. Therefore, matrix A is decomposed into 3 parts naturally. if X and Y are connected in this way, then we say A minus YX equal 1, otherwise 0. In that way, we can define A plus A minus A0. Here is the important part. That Hilbert space gamma G is not necessarily invariant under the actions of this A plus A minus A0. But if gamma is invariant, we can apply the technique of interacting Fock space, that is the basic quantum probability space. Or almost equivalently, we can apply orthogonal polynomial. I will show you. And if gamma G is asymptotically invariant, because we are interested in growing graph, therefore each finite part is not necessarily invariant, but if going to infinity, the fluctuation part disappear, then we can apply. So these two cases, we can apply that technique. Okay, I will show you a little bit more. So here is a theorem. When gamma G is invariant under the A plus minus 0, it is very easy from the combinatorics. The number of such vertices is constant on each Dn. Here you are X, there are neighbors. These numbers are constant, independent of the choice of X in this subset. Such situation happens, then the gamma G is invariant. Then A plus action send this vector to the next one with some scalars. A minus send this vector with some scalars. But because of the mutually self, A plus star is A minus also. Therefore, the number given by the same sequence. And A0 action like this. Therefore, we have omega sequence and alpha sequence, naturally arising from the combinatorial structure of the graph. By the way, this structure is called interacting Fock space. Now, interacting Fock space is very closely related to orthogonal polynomials. So the first line is an interacting Fock space structure, as we mentioned. A is decomposed into 3 parts, and each part we have already the actions like that. And using omega and alpha sequence, we can define the polynomials, monic polynomials like that. 1, x minus alpha 1, and x times Tn. This is the famous 3-term recurrence relation. Then, if we take the orthogonalizing probability distribution mu, always exists for such polynomial, we can define the isometry U, gamma G to L2, by making correspondence between 2 systems of orthonormal basis. Then we can do that UA U star is just the X multiplication operator. This operator appearing here. Then mth moment of A in this vector is equal to this because of this. Because U is isometry. And then you just get this. The P0 is 1, therefore this is the integral. In that way, the vector distribution A is this mu. But that mu is the orthogonalizing probability distribution of this polynomial. So now we end the story. So here, graph structure, you can get omega and alpha from combinatorial observation for others. Then we get spectral distribution.
What is this here? What is this here?
Theorem is if gamma G is invariant, A plus minus, this is the assumption. Then the vacuum spectral distribution mu is defined by this. And this mu is obtained as orthogonalizing probability distribution. Actually, we have analytic part. I just showed two lines how to really get probability distribution mu from that sequence omega and alpha. We have so-called Cauchy transform of probability distribution mu. Then it is known that this function admits a continued fraction expansion like this. This one. Okay, this is very space. We need a lot of space here, so we usually here minus. And that is a classical result. And then if you could compute continued fraction for given omega and alpha, you get this polymorphic function. Therefore, we can invert to get mu. And also there is a formula that is just inversion formula. And from this G mu, we can get mu by using this formula. So this part is an appendix to my book, but anyway, there is some formulas. Okay, now one example. I like this example. This is a homogeneous tree. Degree 4. Tree. There is no cycle, so it is called a tree. And this is stratification. There is there. This one is. And look at that picture. You can immediately get this formula. This kappa is just a degree. From this, we see the omega sequence is kappa and kappa minus 1 afterwards. And after alpha, 0. So we get such a constant from that picture. And then we compute continuous fraction. In that case, computation is very simple. We get simply this function. And we apply inversion formula to get density. And this density is called Kesten measure. And this is a very famous result of Kesten in 1959. He computed spectrum of transition probability of the random walk on tree. And if you take the limit kappa infinity, then we get 10 cycle. This is nothing else but free. In that way, we can apply our technique to get spectral distribution. Okay, now time is almost coming to the end. So, okay, this is another example. And also, distance linear graphs is very suitable to this. Okay. And also, I obtained a general formula for growing families. So this case has distance linear graphs. Maybe I will. Okay, now I will stop maybe with this example. Probably you are wondering, how about the square lattice? Square lattice is a very fundamental example of graph. This is a two-dimensional square lattice. Here we pick origin. This is the first set having distance 1 from here. Next one is distance 2. For the next one, distance 3. Okay. But then we have problem. That gamma Hilbert space is not invariant because this point and this point has different property. This point has 3 edges going outside, but here only 2 edges going outside. So not homogeneous. But as you see, mostly generic part is the same. Sometimes appearing some similar part. But the number of similar parts is much less than generic part, you can imagine. And it is proved that the action A plus A minus almost the first part and some error for terms. Therefore, if you divide square root 2n, that is actually variance. then the limit is exactly given by these actions. Error term disappeared in the limit because of this factor. And the limit structure is well known as boson-Fock space. That is a quantum mechanical terminology. But we know, here I don't go into the computation, but it is known that in the boson-Fock space, the vacuum distribution is Gaussian. So this is the Gaussian distribution. Therefore, the asymptotic spectra of Gn, but n going to infinity, dimension going to infinity. That case, the spectral distribution is Gaussian. And that case is also we can apply the technique of quantum decomposition. Okay, this is just a growing linear graph case, but maybe omit it.
But in 3 or 4 dimensional
Yes.
space, what will happen with the cubes or cubes, simplexes?
Yes, but that is the limit as n tends to infinity. Dimension going to infinity.
Dimension of what?
Dimension of the lattice.
Oh, okay, good.
Okay. So,
Fine.
okay. So this is just a schema of my talk today. So here is the adjacency matrix, and I like to get a spectral distribution. Maybe we can, if you have a finite graph, then you employ the technique of linear algebra or combinatorics. You get spectral distribution. And after that, we can take a scaling limit, we get mu. So this is like a classical method. But today, I introduced quantum probabilistic techniques. So adjacency matrix, maybe some case, the adjacency matrix is decomposed into some parts. And if they are independent in some sense, then we can apply quantum centralism theorem to get this distribution. That is one use of non-commutative structure. Another one is the adjacency matrix always decomposed into 3 parts. But if the gamma Hilbert space is invariant, then we can get interacting Fock space. And this is almost equivalent to orthogonal polynomial. So via orthogonal polynomial, we can get asymptotic distribution. This is another way of computing spectral distribution using non-commutativity. And sometimes non-commutativity is useful to see the link. That is my main message today. And this is the last slide. So I like to develop more. So we are interested in growing graphs. How to formulate a growing graph? That is my question. Basic question. Probably AN apply something else. So in the classical probability, we say this kind of structure typically independent increment process. But here are matrices. So here are certain matrix operations. And if Bn is independent or some special relation to An, then something new happens and we get the next one. So if you could formulate in that way for a growing graph, then maybe we can hope that the limit distribution is obtained from the central limit theorem. So, but this central limit theorem is of course with quotation marks because that is not a usual one. And also, second subject is to extend the method of quantum decomposition. So quantum decomposition works very well for certain class of growing graphs. But that is heavily based on the orthogonal polynomials in one variable. How about 2 variable case? That is a very interesting question now. So I try something. And some trials are given by strongly linear graph and so. But this is work in progress. If you have some idea, I am very happy to discuss. Okay, that's all. Thank you very much for your time.